Hi there, and welcome to our final video of new material for TTED 3044. We spent a lot of time in this course talking about the properties of steel. Steel is a very important metal in industry, but the hardening mechanisms in steel and how it behaves are very unique to the iron-carbon phase system. We're going to review them a little bit here, but we're also going to take a look at a different hardening mechanism, one that's used in aluminum. And in fact, you'll see it happening in other alloys where the hardening elements, the atoms, are about the same size as each other. So in steel, you've got these giant iron atoms and these little carbon atoms tucked in. It's kind of like having baseballs tucked in between basketballs. But when you're dealing with aluminum and other precipitation hardening alloys, you've got alloy elements that are about the same size that are causing the hardening, kind of more like having volleyballs tucked in with basketballs. And the stacking and the ordering and how these behave are quite a bit different. So let's uh, let's go on and do a little bit of review of what's going on in steel, and then let's take a look at what's happening in aluminum because it's almost exactly the opposite of what you'd expect based on steel. Okay, so steel. Primary alloy element is carbon, and as I was just saying, that's like having baseballs tucked in with basketballs. The carbon is the baseball, the iron is the basketball. Okay, it fits into the interstitial voids between them. Not so much when you're at cold temperatures and in the ferrite phase, but above 723 degrees Celsius, you switch into that austenite phase, and you change from a body-centered cubic to a face-centered cubic. You lose your magnetism, and now the carbon fits in between there and can diffuse evenly throughout your metal. So when you've heated that up, your austenite can hold 2% carbon in solution. Okay, so dissolved evenly everywhere. Whereas when we cool down, the ferrite really 0.2% carbon. That's not very much at all. Okay, now when you heat that steel, you're going, I think that's supposed to be 0.02%. I'll have to go back and look at my phase diagram. Anyway, when you heat the steel, heating the steel places carbon into the voids between the iron atoms. And when you cool it, then it has to come out of those voids. And yeah, here's our phase diagram right here that explains everything that's going on. And if we take a look right on here, oh, my mouse isn't showing up on the screen right here. Just a minute. There we go. Now we've got the mouse on here, and I think I can even doodle on the screen if I want. And so the mouse is showing up right in here. So this is our low temperature range right down here at the bottom. This is where our ferrite is. As we get more and more carbon coming in here, we start shifting into more and more cementite. If we get above this point right in here, we're no longer dealing with steel. This is kind of a boundary right here at about 2% carbon, where we shift from having steel into having cast iron. So anyways, in here, we've got different temperatures at which everything translates, everything shifts into the austenite phase. And you'll recall when we did our lab for some of our higher carbon content, instead of just heating up to 723 degrees, we had to heat up to like 950 degrees so that we'd get above this line and transfer everything into austenite and dissolve all of the cementite. Okay, so as we cool our low carbon steels down, they come through this slush zone right here, as I call it, and you'll start to get ferrite precipitating first, and then you'll have these ferrite crystals, and then when you get down to the transition line, anything that's left is going to translate into perlite, a combination of soft ferrite and hard cementite laminated together into layers. Now, that's for slow cooling, and that's how things go. We've been over this once or twice. Let's take a look at this and how what goes on in here. Here's a nice picture right up here of some perlite. You can see the black lines are cementite, the white lines are ferrite, and these have grown inside the old austenite crystals that were left behind. So they're at all different orientations, because keep in mind, when we take a look at a photomicrograph of the steel, we've just sliced it, and so we've taken a chunk and at some orientation we've cut through it and we split the crystals in half, and they're all kind of randomly oriented in different directions. If we've only cooled it, if you've work hardened it, or if you've done specific things, you can reorient some of the crystal growth, elongate it in certain directions, and that's another way to manipulate the properties that's beyond the course contents of this course. So there you have a nice perlite structure, and a combination of soft ferrite, brittle cementite, and thermodynamics, the math behind physics and the math behind the physics and chemistry in your steel and in any chemical reaction. Thermodynamics is forcing it to grow into layers like that. And again, you can do the math and you can calculate why it forms into beautiful layers like that. Uh, we've we've got all of that proven and we know it. But again, you don't need to know that for teaching high school shop classes. You just need to be able to tell students that, hey, we get this, these two things working together, and this is why carbon makes your steel a little bit harder, because it forms this cementite stuff, and you get more of it. Now, this is slow cooling. This is annealing, and actually, there's some websites that are pretty useful for taking a look at that, and I've got them open right here, and I'm just going to pop over here, and let's take a look at two different materials cooling at two different rates. So you can follow those links right through there and take a look. You have to have Adobe Flash running on your system. And what you can do right here is there's your simplified version of the phase diagram. This is what we call a hypoeutectoid. So hypoeutectoid means that we're below this 0.8, the 80 points of carbon line, where we start going back up on this side of the phase diagram. This is our eutectoid point. Hypo means below that point. And so these two buttons over here let you decrease the temperature. Now we're starting out as austenite, and in austenite we've got the carbon all dissolved evenly throughout the steel. And as we start to drop that temperature, and I'm clicking on the decrease temperature button, and you can see us moving down the chart right here, we start to approach the slush zone. Now, when we hit the slush zone right there, you can see it flashes up a little pink line. And if you're using this link and you're reading the descriptions that come along beneath it, it tells you what's going on. And right here, you can see little dots starting to form. And those little dots that usually form at the grain boundaries, because those are thermodynamically slightly higher energy spaces, those little dots that start to form right in there are pure ferrite crystal dots. Now, right here, we don't have very much of them, but as we come down here, we keep getting more and more of them. Now, this little purple line right on here, you'll notice we've got this dot is basically staying at 0. It's increasing just a hair. There is a tiny little zone. That's how much carbon you can fit into the body-centered crystal structure and still have it be dissolved. That means that these dark yellow dots right here are the pure ferrite that's starting to grow at the grain boundaries. Okay, so those are new crystals of ferrite that are growing right in there. Now, as this pure ferrite starts to grow, your average carbon composition is right in here where the red arrow points. And as these areas of basically 0 carbon start to form, out on this side, you've got areas that are going to have an increasing concentration of carbon, because right over here, these dark yellow bits are squeezing out their carbon and purging them into the remaining yellow. So the carbon concentration in this area is gradually increasing as these new pure ferrite crystals grow. As we keep decreasing that, those crystals get larger and larger, and eventually they squeeze the remaining carbon out to the point where the steel right here that hasn't transformed yet has reached the eutectoid point, the 0.8% carbon. So this steel right here is pure ferrite. It's the softest steel, but well, it's not even really steel anymore. It's just iron. This is very close to pure iron right in here. This in the light yellow is close to 1080. So this is actually going to be a high carbon steel. This is an ultra low carbon steel. In fact, it's not even really steel because it doesn't have much carbon in it. At a microscopic level, we've got these areas of very soft material. And right in here, when we cool that down a little bit, we hit that grain boundary, and this stuff says, right, I'm coming through right here, time for me to transition. And now we get that perlite starting to form, and as soon as we're down below 723 degrees, bang, there we go. We've got perlite surrounding the ferrite. And now it doesn't matter how cool we go down after that because the transition is finished. So that's where the microstructure in a low carbon steel is coming from. Now, in a high carbon steel, it works kind of similar, except the temperature gets heated up a little bit higher to make sure everything's dissolved. And then we start cooling it down, and there's really no slush zone right there. So if you have exactly a eutectoid steel, which officially is like 0.83% carbon, but I'm not going to get fussy if they say 0.80, that's close enough. That matches up nicely with what we'd call a 1080 steel. And you come right down here, there's no slush zone to go through. You hit 723 degrees and bang. Now it's all in a rush to start growing. And you pause there for a little while because you're giving off heat while all this is growing, and you end up with a 100% paralytic microstructure. And 100% perlite is just sort of on the border between Rockwell B and Rockwell C hardness. So you're probably looking at a low Rockwell C reading or something in the 100s on Rockwell B when you're shifting over into pure perlite. That's about as soft as you can get a 1080 to go, and it's soft because everything's cooled down slowly and had a chance to find a comfortable place to come to its resting point after the heating and cooling process. Now, when you cool it rapidly, the carbon doesn't have time to move and diffuse like that. And I think I've told you the story where the student, I'm putting notes up on the board at the end of the class, and I add the low carbon steel can't get hard comment, and student whips up his hand and says, Mr. Brad, don't you have that problem too, sir? I won in the end. He learned not to speak like that because I walked over behind him and patted him on the shoulder and said, yes, and we're going to keep that our little secret. And he didn't understand why everybody was now laughing at him. So anyways, there's delightful moments like that in teaching, and yeah, you can tell it still brings joy to my mouth, joy to my face to smile. Joy to my mouth, what the brings joy to my life, to think back on some of those fun moments in teaching where you help young people learn to develop and refine their sense of humor and think about what might somebody say next after I open my mouth and get yappy with them. Anyway, a little off topic. So low carbon steel can't get hard because there's not enough carbon to actually get trapped anywhere, and you're not forming cementite. What you want is when you rapidly cool it, you want those carbon atoms to get trapped in between this expected, you've got this austenite structure, and then the carbon can't get out of it, so you can't really form ferrite, but you've got to do something because you can't stay as austenite, and the entire structure just goes crank like this, and you end up with kind of a new crystal structure that's really a distorted body-centered cubic trying not to be body-centered cubic because you've got all these damn carbon atoms in the way, and this distorted, warped, stressed out structure is what forms martensite and another phase called bainite. But we will focus on martensite because that's the harder of the two. So it's very hard, very brittle. The atomic bonds are all stretched to their limit. And so when you got your high Rockwell C readings, so anything in about a Rockwell C mid 50s through 65, which is as hard as you can go in steel. So when you're putting uh, numbers like that out on the Rockwell hardness machine, you've got martensite in there. And as you get harder, you've got higher carbon martensite because you've got more and more carbon trapped right in there. You can get a low carbon martensite in some of your low carbon steels. You don't get very much of it, and it's not as hard as that high carbon martensite. The high carbon martensite's really warped, really stressed, really hard, very high yield strength, but very brittle. Okay, because it's already been stretched as far as it can go at a microscopic level. There's nothing left for it to give. There's nowhere for it to go. So, so that's what happens when we cool it rapidly. And then we take it back and we do this process called tempering, somewhere around 300 degrees Celsius, somewhere in there. And you heat things up. And this is our opera versus the nightclub analogy. At low temperature, you're at the opera. Everybody's sitting in their seat and, very relaxed and very serious. And then you heat things up and you're at the nightclub and everybody's moving around and the atoms are able to move. They haven't changed phase yet, but at least they're able to move around. And the most stressed carbon atoms will get bumped over here into a less stressed place. And that means that you give up a little bit of hardness, but you gain a lot of toughness in the process. And the time and the temperature that you do your tempering for really do matter. And you can either give up a lot of hardness and gain a lot of toughness, or you can give up a little bit of hardness and gain a little bit of toughness. And there's some sweet spots in there, also some nasty spots that you want to avoid. So you kind of have to understand what works for your steel. Different steels will have different optimal times and temperatures for tempering. And the key thing is that you know to look that up. You don't need to know off the top of your head right now. You just need to know that that's out there and you should be paying attention for that. Yeah, here's our crowded dance floor analogy. This is why this works. And medium temperatures, of course, like we're doing in tempering, are allowing for controlled diffusion. And this atomic diffusion is a really important part of what's going to happen in aluminum. So the basic thermodynamics and the basic physics are the same. You just have to keep in mind that aluminum is going to be different because the atoms that are doing the hardening are about the same size as the aluminum atoms. Okay, you've got some copper and some aluminum in there. It's kind of like volleyballs and basketballs. Whereas with your steel, you've got carbon, which is really tiny, and iron, which is fairly big, kind of like baseballs and basketballs when you're putting them all together. Let's, before we talk about aluminum, let's also talk about something that you may be familiar with, okay? And this is growing crystals for a science experiment in elementary school, or as a more adult way to look at it, mixing up a simple syrup for your bartending needs. Okay, a simple syrup is just a saturated sugar solution. And we've got these terms called saturated and supersaturated that are going to be really important when we talk about aluminum. Okay, so think about putting sugar into cold water or salt into cold water. It really doesn't dissolve well at all. Okay, the water's cold, the atoms aren't moving around very fast. It will eventually dissolve, of course, but it's really got no incentive to get around to doing that very quickly because the energy level is low. It's cold, right? We kind of feel that way in winter sometimes. It's cold, it's blah, don't want to go do anything. Summertime comes, it's fun, it's hot, let's go outside and let's party. The temperature differences, of course, that we treat our sugar to are a little bit higher than we want to experience ourselves, but let's go with it. So now what happens is that if you've put in enough sugar that you can't dissolve anymore, and you keep stirring it and you keep adding sugar and you start to see the sugar building up on the bottom of the cup, that water's not able to hold any more sugar. If you heat it up, however, Now the atoms are moving a little bit more, and there's a little more incentive for the sugar to dissolve. So the sugar will start to dissolve, and at 50 degrees, you'll be able to dissolve a certain amount of sugar. And at 60 degrees, you'll be able to dissolve a little bit more sugar. And at 70 degrees, you'll be able to dissolve more sugar. And 80 and 90 and 100 and 110. And if you figure out how to get your water up to 110 in a pot, let me know. You're obviously, operating in a submarine or something like that, because water boils at 100 degrees under standard kitchen temperatures and pressures. Alrighty. When you've got boiling water, that's the most sugar that you can possibly fit in your kitchen situation, and it holds a lot more sugar than it does when it's cold, because you can just keep scooping it in. And you think about how easily sugar dissolves in your coffee versus how easily it dissolves in cold water, and you've got a very practical example of that happening. Now, you boil the water up, and you've got boiling water, and you just keep adding sugar and adding sugar and adding sugar until a little bit of sugar gets left on the bottom right there. And just before that last little bit of sugar got left on the bottom and it couldn't dissolve anymore, you're at what we call a saturated solution. So a saturated solution is when the solute, the solvent, the water, can hold no more solute, the sugar. Okay, you've got your solvent and your solute. The solvent is what's doing the dissolving. The solute is what's being dissolved. Always good to know those words if you're into crosswords. Jeopardy, maybe. Anyway, let's carry on with this. So now you've got this super saturated sugar solution, very, very high in sugar, and it's going to be viscous and sticky. It's going to be almost kind of like honey. And then you start to cool it. That's where interesting things start to happen, because as you cool that solution, it can no longer hold that much sugar in solution. Now, as you start cooling it at first, the water's like, I want to get rid of some of this sugar. Now, I've got too much sugar in here. But if it doesn't have anywhere to put it, you can actually drive the solution quite a way down, and you can cool a lot of it off and still retain it in what's now a supersaturated solution. So if everything is perfectly clean and there's no nucleation sites, okay, or no structures or lattices for the sugar to start crystallizing, you can actually keep that sugar in solution for a long time. And you can end up with a supersaturated solution, which is really sticky and thick and viscous. And then when you drop a crystal of solid sugar into it, that will form a nucleation site where all of a sudden, all the supersaturated sugar in solution is going to say, oh, I can fit onto this crystal right here. And I can fit onto this crystal right here, and I can fit on this crystal right here, and it will start to come out of solution, and it will start growing a sugar crystal. And so, yeah, if you haven't tried it, give it a shot and grow yourself some sugar crystals. There's all sorts of neat little crystal growing experiments you can do at home. Controlling the temperature and the concentration of sugar that you have can control the shape and size of your crystals. Slow cooling is going to give more time for all of the sugar to come out of solution and arrange itself neatly around the crystal, and you'll tend to get larger crystals if you cool things slowly. Now, why all this talk about sugar? Because the terms saturated and supersaturated and solvent and solution are all going to apply to our 6061 aluminum alloy, because that's how it hardens. Now, in 6061, which is one of many aluminum alloys that are available, but probably one of the most common ones that you'll see in the shop, you've got some main alloy components in there that are involved in the hardening. So in iron, the importance of carbon was so fundamental that we didn't talk about all the other alloy elements that happen in steel. Okay, just carbon is so important to steel, we skipped over everything else. Precipitation hardening that we're talking about for aluminum also happens in steel, which is why there are other alloy elements in steel. But the carbon is so important, we focus all our effort on that and kind of ignore everything. Um, if you delve deeper into steel, you'll find that all the other alloy elements really do matter a lot. And in aluminum, because we don't have that one dominant hardening mechanism, we are going to end up talking about how all the other alloy elements work together in here. So 6061, our main alloy components are silicon, magnesium, and copper. And as you can see, they're all present at percentages around 1% or less. Okay, you might get a little bit more magnesium in there. It is going to vary from manufacturer to manufacturer and lot to lot, so long as you stay within a certain boundary of high and low concentrations and material properties, you're okay in what you're doing with your aluminum. You're not going to be making aluminum, you're going to be buying it, so it's going to come to you with alloy components, something like this. Now, the key thing about these alloys, as I've said all along, is silicon, magnesium, and copper atoms are all about the same size as an aluminum atom. Now, if they were exactly the same size, they wouldn't be really great. Well, they'd be a great alloy compound, but they wouldn't provide us with any beneficial properties. It's that slight difference in size that's going to help provide some of the strength properties that we're talking about. And when we talk about an aluminum alloy, this is a substitutional alloy where one of the alloy elements will replace one of the one of the alloy atoms will replace one of the aluminum atoms in the crystalline structure. This is different from an interstitial alloy where carbon and steel, like those baseballs and basketballs, fits into the interstitial voids, into the gaps. Here, it's a one-for-one replacement. Somewhere, wherever there's a silicon atom in that aluminum alloy, it has displaced an aluminum atom, and it's just a slightly different size. So let's take a look at what this might look like at an atomic level and what's going to happen when we heat it. Okay, now when we get a piece of 6061 T6, that T6 on the end is a really important piece of information because that means it's coming to you in a tempered condition. Okay, and you can go look up and you can check out the properties of 6061, and the T6 is a very specific state of heat treatment that's already been done to the steel. So it is not at its softest state. And that's a critical thing to know about aluminum because it's different from steel. 99% of the time when you buy steel, it comes into you in its annealed state, which is the softest state that you can get. But in aluminum, you'll usually buy it in a hardened state because even in its hardened state, it's still relatively soft compared to the steels. Okay, if you got steel in its hardened shape, you wouldn't be able to machine it very well. In fact, you'd end up damaging a lot of your tools as soon as you went to try and cut a piece off. Aluminum, it can come out in its hardest possible state, and your steel tools will still cut through it very nicely if they're properly made. Okay, so here we've got two images, and we've got the 6061 after quenching and after aging. And you can see we're looking at atoms right here, and we're going to have all the gray ones right in here are our aluminum atoms, and the little black ones are our alloy elements. And they could be copper, they could be silicon, they could be whatever. You'll notice in this diagram, they've been shown to be slightly, ever so slightly smaller than the aluminum atoms. And so where you have one of them sitting in the lattice, you can see that the aluminum atoms just sort of shift a little bit out of the way to wrap around it. Okay, now when you heat everything up, you end up dissolving all of your alloy elements evenly throughout the aluminum solvent. Okay, so just like our water dissolved our sugar, aluminum dissolves its alloy elements when heated and absorbs them evenly throughout the microstructure. So we end up with individual little atoms just spaced out everywhere and everybody's vibrating together. And that works out great because at high temperatures, you can dissolve a lot of material. Now, as you cool the aluminum, okay, you're going to trap these in place. Now, if you cool it really rapidly, you're going to end up with them trapped kind of like this. And this is why this says after quenching. The hardening process in steel is that quenching process because you're trapping carbon in places where it shouldn't be. In aluminum, this is actually a softening process because what you've done is by heating up, and you don't heat it up nearly as hot as you do the iron in your steel. You heat it up to the point where you just get all of the alloy elements dissolved and equally spread out, and they're sitting there as individual atoms. And as individual atoms, they just cause a little distortion in the microstructure of the crystal, and they really don't add that much strength. But they don't like being individual atoms at low temperatures. Just like the sugar would start to grow crystals because the solution is supersaturated, your aluminum wants to start growing crystals too. Well, your alloy elements inside the aluminum. The aluminum's not particularly thrilled to have all these little black dots in between its nice rows of lovely gray dots. And so what happens is if you give enough time at enough temperature, then your alloy atoms will start to vibrate through the mesh, and they will join together and they will form what we call precipitates. Okay, their own microcrystal inside the larger crystal of aluminum. And these precipitates are really useful because when it comes time for somebody to apply stress to the aluminum and your atoms are being stressed and trying to slip past each other, well, when you have a perfectly clean grid like this and you start slipping, they just keep on slipping and slipping and slipping, and it's pretty soft and easy to do. But in something like this, now you've got slightly mismatched patterns of atoms, and this precipitate right in here actually blocks the slip planes in all these different directions from sliding right through it. Now, eventually, if you push hard enough, you can get enough force to either have your slip go around the precipitate, or you can actually go through and slice the precipitate, but it takes a lot more work than when you've just got this nice, neat row of aluminum atoms lined up right here. A vacancy is a space where, just due to the random nature of everything that's happened in there, sometimes you end up with a space where an atom really should go, but it didn't happen because everything got quenched. And so there's a couple right here around each vacancy. You can see the atoms are kind of like, oh, I should be over there. Well, if you give it enough time at enough temperature, eventually you'll get rid of those vacancies and everything will vibrate around and your alloy elements will form into tiny little precipitates. The precipitates in aluminum are what helps make it strong. So when you quench 6061, you trap the alloy elements in their individual one-off state. The atoms are dispersed evenly throughout the aluminum. They haven't had a chance to form those precipitates that block the slip planes. And this results in a soft ductile aluminum. In fact, that piece of 6061 T6 that you buy from the from Metal Supermarket or wherever you're buying it, that 6061 T6, if you heat it and quench it, it's going to be 1/3 the yield strength. You're giving up 66% of your strength by heating aluminum and cooling it. Let's take a look at what that looks like. In fact, I went and we did some very sophisticated testing. And I went out and we've used the Rockwell machine, and there's a Rockwell tester, and I talked about the fact that there was a Burnell tester and a Vickers tester. I went out and I got the highest quality, fanciest sample that you could get.
Primer grip strength
The
into
Tony
this,
testing
and
machine.
I've given him a piece of aluminum 6061 T6, and it is just not budging for him. Okay.
I did put a bit of a bow in it.
Did you get a little bit of a bow in there?
Actually.
Oh, perfect. That's exactly what I'm looking for. Okay, I'm going to go heat that up, cool it down, and I'll be back in a minute.
Cool.
Thank you to Tony for going and putting an effort into that piece of 6061 T6. So that was the hardened aluminum. And, you know, I went and found, you know, I picked a guy with pretty good grip strength. He's a climber, you know, he's going to be able to bend that if it's going to bend. And honestly, I think I've had like one person in the entire time I've been doing this lab actually able to take a piece of 6061 T6 and hulk their way through it. It was a pretty big guy who was able to do that. And he was turning pretty bright red. So anyways, what did I do with that piece of 6061 T6? Well, I went and heated it up.
And now we're just going to make this a little more amenable for the Tony test here. We're gently heating this up, and it's going to take me a while to do because I've got to get it up to temperature. But when you're welding aluminum and things like that, if you start with a 6061 T6, you want to keep in mind that even gentle heating can have a big impact on its properties. And what we're going to do is a quench and temper on here. So we're going to heat it up, not to the same degree that we heated up the aluminum, because we're not doing a phase change or anything here, or the iron I should say, because we're not trying for a phase change here. This is something completely different. We don't get it into the glowing range. Take this and heat it up for a little while, then we're going to quench it and go back and see what happens to during the Tony test.
Okay, so they're using just a propane torch, nothing fancy, okay? Don't use your oxyacetylene, that'll get too hot, you'll end up melting the aluminum. You'll be sitting there using the oxyacetylene, waiting for it to start glowing like you want the steel to glow, and before the aluminum starts to glow, it will melt. It's got a much lower melting point, so just a nice little propane torch. In fact, even a really good heat gun could probably heat your steel up hot enough. Heat your aluminum up hot enough. Now, what that is doing to us right there is that in our aluminum, we are diffusing all of those alloy elements. So when I was putting that torch on it, it was just like boiling water. And boiling water can hold more sugar, so the sugar atoms diffuse and spread out everywhere. This is a solid solution, but the same thermodynamics apply. You're heating up the material, and it is able to diffuse the alloy elements everywhere. Okay, so now we've got these individual atoms sitting in the aluminum, and so just as in the steel, we did some
So we've heated it up,
quenching,
and now we quench it down.
I thought I'd be nice and cool it off before I gave it back to Tony for a second test. Because it doesn't look that hot.
When we put it in there. But we'll see if it behaves differently.
So that sudden quench that we did right there trapped all of those diffused atoms into the aluminum matrix. Okay, and so now they're stuck in there, and that's given us a soft and ductile material that should be about 1/3 the strength of what the original 6061 T6 alloy is. And so I went back and I found Tony.
Okay, so we've got the same piece of aluminum here ready for the Tony test. It's been heated up and cooled down, and I see it going. He's almost there. Oh, look at that. He's hulking out on it. He's turning red instead of green. Look at that. There it goes. It's still got some strength in it, but look at that. It's definitely gone. He's got it now. He's doing some work hardening to it. Excellent. There
Hey,
we
that's
go.
right. It work hardens. So as I'm bending, it's getting harder.
Hey, I was just worried that we were going to have to upgrade from the Tony test to the Huckle test. There we go. So that is no longer T6. We have softened that by quenching it.
So there you go. The strength of a quenched and tempered piece of 6061 T6 is almost exactly 1 Tony for its yield strength. Uh, and this from the guy who likes metric units. So anyway, what you can do with that piece after you've quenched it is you can go and deform it quite a bit. And I just wanted to show you the difference in how much you can deform it. I say it's soft and ductile. Well, let's take a look here. This will give you an idea of just how ductile we're talking about. Let's see right here.
Okay, Chris here has volunteered to help show what happens to the 6061 T6 when you take the T6 off of it. And there we go, big beautiful hook right on there. Arr, matey. So here we go, this is the same length and the same material, it just hasn't been heat treated. And there goes the vise, or the handle, it's coming up. So it's not going anywhere. Now, I grabbed a hammer and beat the snot out of it to get it going. So let's grab a hammer on here. Oh, yeah, go that way with it maybe. Oh, he's got it. He's got it. Look at that. He's able to make it move a little bit. He's got it going. Ah, beauty. And look what happened to it right there. It didn't bend, it broke under his massive onslaught of power there, and that shows that although the yield strength is much higher, the strain to failure is lower, and overall, Chris can snap the 6061 T6.
I can snap it.
And you can see it pulling apart right in there, and so much, much higher yield strength, higher hardness, but maybe lower toughness, because if you compare those two samples, the sample with the lower yield strength, really, let me just zoom in right there. And so this is the non-heat treated sample, and you can see, yeah, it's just ripped apart, and on there, actually we can take that sample right there, and you can straighten it out even if you want a little bit.
Let's see.
So there we go, look at that, it comes straight, and you can bend it back the other way. We've basically turned that piece of aluminum into a wet noodle, or the aluminum equivalent of a wet noodle, I guess. Alrighty.
Oh, right, I meant to edit this section out.
Wasn't supposed to. Thank you very much.
That Right, anyway, yeah, you go to hit the off button and you hit the selfie button by mistake. And anyway, so that is part of a lab that we would normally do. And we'd actually take our sample. You guys would have machined samples specific for a tensile testing machine. And we'd actually put them in the tensile testing machine and we would rip them apart slowly and painfully. And the 6061 T6 would require like close to 10,000 pounds, about 5,000 kilos, 5,000 kilos times 10 is be 50,000 newtons in order to pull apart. Whereas now, I use the term heat treated. The 6061 T6, when it comes to us, is heat treated. Okay. We then applied our own heat treatment to turn it into a softer material, and it's about 1/3 the strength, but you can see how far you can stretch it because the ductility's gone up, because now those slip planes are able to slide across each other, and they just keep sliding and they keep sliding, and there's really nothing in their way because all of those atoms are diffused, they're dispersed. They're having to work on their own. And really, just like so many things in life, they're much better at blocking slip planes when they all get together and work together. So what we want to do to get that property back and to get our T6 property back is we have to gently reheat it. So in our steel, quench and temper hardens the material, and softening and quenching it, heating it and quenching it in steel hardens the material and makes it more brittle. Then we gently reheat it in a tempering process to give up some of that hardness and regain some toughness. Aluminum is exactly opposite. When we heat and quench our aluminum, it makes it soft and ductile because we've dispersed the alloy elements and trapped them in their dispersed state. Gentle reheating allows them to move through the material, forming new precipitates, and the precipitates get bigger. And those precipitates will block the slip planes for us, making the material harder, but less ductile. So two processes, both alloy processes, but because steel is so focused on the small carbon atom and the giant aluminum atom in comparison, or sorry, the giant iron atom in comparison, whereas aluminum is focused on similarly sized atoms, you get completely different behaviors because the hardening process depends on a different thermodynamic, different chemical reaction. So why is this all happening? Well, your plastic deformation, okay, which is what happens when you exceed your yield point, is caused by dislocations traveling through the crystals. And those dislocations are just, planes slipping past each other essentially, and that only stops when you run into something. Now, it could be a grain boundary, and you'll see people talk about the importance of grain size in both, grain size is another word for crystal size, in both aluminum and in steel. That matters, okay? Because when you hit a grain boundary, that can serve as a block. But you've only got so many grain boundaries, and you see that happening in work hardening, but you've only got so many that will only do so much for you. But the precipitates that we form also stop the dislocation from moving. And based on your alloy concentration, you can get a trade-off of either having many small precipitates or a few large precipitates, and your thermal history determines whether you've got many small ones because everything's closer to that quench state where it's been completely diffused, or a few large ones. If you go too far, though, you just end up with like one big precipitate and everything goes around it. And that's why it's important to have your time and temperature for your heating process right in order to get the perfect precipitate. If your precipitates are too small, they're not big enough to actually block the slip planes, and the dislocations will pass around them. And this is what you run into when our heated and quenched 6061 was soft. Now, if you overage something and you overdo it, the giant precipitates become too rare. There's not enough of them to block all the different slip planes, and the dislocations, might stop when they run right into them right there. But 3 atoms over, there's a whole range of atoms that just keep on slipping right around that, and you don't have another particle precipitate over here blocking things. Okay, you've got all your forces right here and saying, okay, I'm blocking these slip planes really well, but I'm completely ignoring those ones. So you need to get just the right precipitate size. And I kind of make it an analogy that may or may not make sense to you, but I'm big on analogies, so try this one on for size. The perfect precipitate, okay, is going to make it very difficult for the slip planes to travel. And think about gravel. If you've got nice fine particles of gravel on your gravel road, it's really easy for your truck or your car or your bike to ride over top of them, because your wheel is large in relation to the precipitates. Okay, we've all driven down gravel roads. We know, though, as the gravel starts getting larger, that road noise starts to go up, and it starts to be a little more worrisome for our car that maybe you don't want to be going down that fast. And if you were going over gravel that was, I don't know, about baseball sized, you might not be going as fast as you were when it was marble size. And if you get a little bit bigger, now you're getting into the four-wheel drive off-roading type thing. And if you had gravel particles, rocks, we'll call them, that were about the same size as your wheel, well, you'd be going up and down. You'd be going along, if you were going at all, you'd be in a four-wheel drive with raised, suspension, and you'd be going pretty slowly to get over top of that if the gravel particles were all the size of your wheel. But if you kept making those gravel particles bigger and bigger and bigger, and now you had a gravel particle that was the size of, I don't know, a mountain, okay, you'd have smooth surfaces on that gravel particle because it's now much larger than your wheel, and your vehicle's going to be able to drive right over top of those smooth surfaces, and you're back to moving on a smooth surface at high speed. So that's kind of like your precipitates. If they're too small, they don't slow things down in terms of travel. They don't block those slip planes. If they're too big, there's not enough of them to block the slip planes, and you can get these nice smooth pathways that go zooming past all of the rough bits. And so you've got a perfect precipitate size in there for a perfect set of materials, and time and temperature are going to help you control what you get for your precipitate size. And here's kind of the results that you see, your strength right here, okay, in comparison to the size of your precipitate is really matters. Here's the size of your precipitate coming along here, and your maximum strength is going to be achieved where bowing, the nature of having too few precipitates and the dislocations going around it, run into the cutting strength where you just slice past the precipitates. And in here, you've got a critical radius that gives you your highest strength material. And so, in other words, there's one particular size of precipitate that makes things really annoying for the slip planes trying to move anywhere. So let's see, a couple of things that we can take a look at right here. Now, when we do this lab for real, and this year in 2020, we've had to make some changes to our schedule, so we haven't done that. But when we do this lab for real, what we'll actually do is we'll take some of our aluminum samples right after we quench them. And when the precipitates are all diffused, and we'll throw them into the freezer and keep them at the lowest temperature we can. If I had liquid nitrogen sitting around, I'd throw them into liquid nitrogen, and that should really slow those atoms down and keep any diffusion from happening inside there. We'll take one sample or a number of samples, and we'll do what's called a room temperature heat treatment. And yeah, we might put them on a heating element or something just to get them up to 30 or 40 degrees, but basically we leave them sitting in your locker. Room temperature is actually a temperature, and there is some vibration of the atoms when you're at room temperature, and you do get some precipitate growth happening at room temperature. So your aluminum, that piece that Tony was able to take and bend, if I went back a week later with that same piece, or a piece similar to it, he'd already bent that one, obviously, but if I went back and I had two pieces exactly the same, and as soon as I quenched it, he goes, oh, and he bends it. If I'd waited a week and I brought it back to him, he probably wouldn't have been able to bend that. Because just sitting still at room temperature, those atoms are going to be vibrating around a little bit, and they're going to start growing slightly larger precipitates, and you're going to get closer to that critical radius, and you're going to get a harder and slightly less ductile material. Now, if we bake the aluminum at about cookie temperatures. Okay, and this is actually the assignment I send students home. I say, take your piece of aluminum. Anybody baking bread or baking cookies or roasting a turkey this weekend? Fire the aluminum in there, and that will artificially age it. And you'll get close to the T6 state. Maybe not exactly a T6 state, but we'll take a look at the times and temperatures to get you close to T6. There's a few things that are going on to get a true T6 state that are a little bit more sophisticated than this, but the general concept is that you'll get most of that T6 strength back with a little bit of artificial aging. But it's the room temperature hardening that really blows my mind, that you can take a piece of aluminum and just leave it sitting there for a week and have it get harder and stronger all by itself. I wish I had an exercise plan like that. Sit on the furnace for a week and you'll be twice as strong by the end of the week. This was actually a really neat trick that was used in the manufacture of airplanes. Pop rivets, if you think about aluminum pop rivets, they would make aluminum pop rivets, they'd heat them and quench them and store them frozen. Now, because they've been heated and quenched, frozen, they lock in that diffuse state, and they're still ductile and they're still relatively soft. And they take the rivet, they put it into the airplane, they'd pound the backside of it, and because it's a rivet, you want to be able to form that head nicely, so you want a soft ductile material. And then they'd let it sit in the plane for a week. Well, when your plane takes off, you don't want soft ductile rivets, but the alloy that they used would naturally age harden over the course of that week. And that soft ductile aluminum that they were able to form a nice round rivet head with would now become a hard aluminum that was capable of holding the airplane together. Neat material properties. A practical place where you might see this and use this in your shop is quite often your sheet aluminum will come in as 6061 T6 sheet aluminum. And when you go to bend that sheet in the box and pan brake, you don't want to bend it to too tight a radius because it will crack, just like that piece that Chris was putting into the anvil. And all of a sudden, all of your sheet metal cutting and everything, as you go and bend it in the box and pan brake, and crack, there it goes. You don't want that. So what you could do is along that piece where you know that you're going to be folding things up, you could heat it up with a propane torch. Okay, just gently heat it up, get everything good and hot in there. You could quench it. You could do your bend. Let it sit there for a week. And now it won't be quite as strong as the T6, but you'll actually be able to make nicer bends in your 6061 T6 sheet metal and regain some of the strength that you've given up. Now, on the other hand, if you're welding the 6061 T6, you've got to appreciate that you're doing some pretty serious heat treatment when you do your welding. And whatever used to be T6 after you weld is no longer going to be T6. So you will be giving up some strength in there unless you go through an entire heat treatment process for your entire piece of aluminum. So just beware, just as with your welding a high carbon steel, you can get something that it has a high yield strength but is brittle. If you weld a 6061 T6 aluminum, you can get something that is lower strength but more ductile as a result. And that will affect the entire heat affected zone of the weld as well as a larger area around that. So it's not just in the weld that's going to be treated itself. Aluminum really distributes heat evenly. Anyway, so what's the perfect time for aging these? So here's your hardness, and the hardness on this chart that I was able to find, and I think I've credited it right down here. The Vickers scale right down here is, anyway, higher numbers are harder. Higher numbers harder indicate higher yield strength. So here's our aging time, and here's our different temperatures right here. So if you put it in at 350 degrees Celsius, that's not going to get you a particularly hard aluminum, and that's because 350 is getting pretty hot. You're actually kind of rediffusing some of that aluminum in there, and you'll see it get softer with time. Whereas if you age it at a lower temperature, 185 degrees C, that's probably close to the 350 Fahrenheit or something that you'd be baking cookies or bread at. And you can see that over time, your strength starts to come up and up and up because you're growing those precipitates, and then whoop, it starts to drop off again because you've grown them too large. And now you don't have as many precipitates, you're not blocking as many slip planes, and things can slide past that. So you'll notice that almost all of these aging temperatures, except for even the very coldest, the 175 right here, drops off at the end because those precipitates get too large. So if you do some welding of 6061 T6 and you need to regain some strength in there, you can leave it sitting out at room temperature for a week, or you can probably get your maximum strength back out of it at about 185 degrees Celsius for somewhere around 6 hours in the oven. If you've only got 2 hours, that seems to work pretty good too. So, why does this matter? Well, first of all, it's like so many things in metallurgy, it's just really cool. Um, that's my definition of cool. Works for me. I'm sure there's other definitions of cool on this planet. But why it matters, what does welding do? Well, welding affects, as we were saying, both steel and aluminum. It's a very brutal heat treatment. Okay. How does your metal respond to high temperature? So if you're using this metal in a high temperature environment, now think of ovens or anything like that, are you going to have the same strength after you've used it a couple times? Your alloy choice is going to be important to that. So when you're talking about aluminum, and I'll just wrap up with a couple of slides summarizing on this. I've been going on for an hour now, probably half an hour if you're playing this back at 2x speed with the closed captions turned on. But our heat treatments demystified. So we always talk about 6061-T6. So the 6061 refers to our alloy. And there's a whole range of different series of aluminum alloys. So we're in the 6000 series, and within the 6000 series, there are other alloys that are available. 6061 happens to be the most common, and the T6 state happens to be the most common heat treatment that you'll buy the aluminum in. But if we heat it all up and then we quench it, so we heat it, we soak it, we remove the effects of the work hardening. This is our -O state. And of course, -O stands for annealed because there's so many O's in annealed. They needed a letter, whatever. 6061-O is annealed, and that drops us down to about 55 megapascals yield strength. That's in comparison, you'll see later on when we get to T6, that you're about 276 megapascals for your yield strength. So, I said 30% later on. That's even down to like 20, 25% of your original strength. If you anneal it just right, wow, it's completely putty. Now, we probably got closer to the 6061-W, which is the solution heat treated, which would have been a little bit stronger. So somewhere around 30% makes sense. And, we heat that up and then we quench it. But you can do it a little bit quicker, whereas the annealed state is a more dedicated, thorough process to really go through and recrystallize absolutely everything in there. It undoes any work hardening that you've done. And basically, it's like giving you a new soft piece of 6061 with all of your precipitates dissolved and just individual atoms of copper and what did I say, silicon, and the other alloy elements distributed amongst the aluminum atom matrix. So then both O and W will have those precipitates start to form at room temperature, and you'll get up to, like I say, a state known as T4, which is the naturally aged state, or one of the lesser known Terminator movies. So 6061 T4 is what you get when you let dash O or dash W sit around for a while. That'll come up to about 145 megapascals, or over half the strength of your T6. But if you want to get back to 6061 T6, throw your aluminum in the oven as you roast a turkey, about 350 degrees for 8 hours, and you'll gently reheat that. You'll regrow some precipitates, and you'll come out at about 276 megapascals yield strength. And that is the magic of metallurgy. As soon as you learn one thing about steel, we take it and we flip it around and make it completely different for aluminum. And we haven't even started to talk about brass and bronze yet, although they're closer to the way aluminum behaves because their atoms are pretty close to the same size and they're substitutional alloys too. There's a lot of really cool stuff going on, and although you can do a deep dive and learn a lot more than you need actually for teaching your basic high school metal classes, I hope you found it interesting and enjoyable, and that you've learned a little bit about why metals matter. Thanks. Where's the stop button anyway? You'd think I'd know this by now. Stop.